I'm Peter Davies. I'm now a lecturer at the University of Surrey, and welcome to my talk on the link between local and low-space MPC. This is partly going to be a survey about what this link is, what's known about it. It's also going to include some of my own recent work with Arthur Tumai and Marav Pata. So wherever I give a citation without names, that's one of our recent works. And I'll start off by quickly talking about what I mean by the distinction between distributed and parallel computing, and how this connection represents a bridge between these two kind of paradigms. So by distributed versus parallel computing in the context of graph algorithms, this being a workshop of graph algorithms, what I mean is that when I think of a distributed graph algorithm, I have my graph, and the thing that makes it distributed is that the computation that's going to be done, however we're solving the problem, we're going to do some computation, and the computation is done in some way which is related to the locality of the graph. So in particular, in the model we're going to be looking at, the nodes of the input graph on which we're solving this problem, are going to be doing the computation. Okay, and the edges in the graph represent some kind of reachability. So machines that directly have cables between them, for example, or within some geographic radius that they can communicate wirelessly. So the edges represent reachability by direct communication, and the nodes are the places where the processing is happening. Whereas for a parallel graph algorithm, the setup that I consider to have is that we are given some graph, and it's probably some big graph, and then separately we are given a bank of processes. And because our graph is so big, we need to solve our graph problem on multiple processes. It's too big to solve it on one. But these multiple processes don't have any a priori relation to any particular part of the graph. They're just a bank of processes. They could all be in the same server. And for example, we just want to apply them efficiently in parallel to solve our problem. Okay, and there's going to have to be some restriction on these. That would mean we couldn't just feed the whole graph into one processor and solve the problem, because obviously that would be the quickest way to do it if that did fit into our hardware capabilities. So some restriction on the models has to say that there's a reason we have to do this in parallel. Okay, so the two particular models that I'm going to look at, one distributed and one parallel, are the local model, Linear's local model from a distributed computing perspective. And as I said, it's going to look very similar to the last slide, but we have some graph, and I'll denote the number of nodes in the graph by n, the number of edges in the graph by m, and the maximum degree in the graph by delta. And on the nodes in the graph are the processes. They are what is going to be solving our graph problem, whatever our graph problem is, on this input graph. And we have synchronous rounds of communication, and in every round of communication, each node can send messages to its neighbors in the graph, the other nodes to which it has direct links. In the local model, we don't have any restriction on these messages, so it can send whatever it likes, as many bits as it likes, it doesn't matter. We also have no restriction on the processing that can be done by any individual processor, so they can do as large a computation as they want locally, but obviously they can only use the information that they have locally. And our goal is then to solve whatever graph problem we're trying to solve using the minimum number of communication rounds. Okay, so basically we want to solve the problem while allowing communication in a smaller radius as possible on this graph. Okay, so that's the distributed model, the local model. And the other model I'm going to be talking about is the MPC model, massively parallel computation, which is our parallel model representative. So what I mean by this model is that we are given again our same graph, n nodes, m edges, maximum degree delta, and we are given a bank of machines, and these machines have a restriction on the space they can store. And this is what prevents us from just putting this graph onto one machine and solving the whole problem on one machine. So they have this space-bound S, and and to make this more trivial, the space-bound S is going to have to be smaller than the total size of the input graph. So the amount of information it takes to store the whole input graph, which is going to be like n plus m, can be as much as n squared. The space S on each machine is going to be less than that, which means we have to solve this problem in parallel across our whole bank of processes. We can't just use one. And to communicate between the processes, it works like this. We get our graph, and to begin with, it's arbitrarily partitioned among the processes. How it's partitioned doesn't really matter. But obviously, this partition is going to have to respect the space-bound S on each machine, because we can't put more information into any machine's memory than S. And then we have, again, synchronous communication rounds. But now, because these machines don't have any proximity relationship. They're not part of the graph. They don't we don't have these links of which machines are close to each other, which aren't. We're allowing all-to-all communication here. So these machines can send information to any other machine, right? Because, as I say, they could be in the same server room, could be right next to each other, and that would probably be the most common way of doing parallel computation. So we have all-to-all communication here. The only restriction on the communication in the communication rounds is that the total communication, the total input and output sent by and received to a machine has to be at most S again, because, as I said, their memory bound is S. They can't send more than S stuff, and they can't meaningfully hear more than S stuff because it has to go into the memory for the next round. Okay, and then they do some local computation, and there's no bound on the computation they can do except that they only have S space. So I mean, you can't usefully do more than exponential in S computation if you only have S space. Most of the algorithms we look at won't use high computation, but in some cases there are parts of our work where high computation does come into it. So we don't bound the computation, we just bound the space in the MPC model. And then we proceed in another synchronous communication bound. And again, our aim is to solve whatever graph problem we're studying using the minimum number of communication rounds. Okay, so I'll just briefly talk about number of machines, but this isn't a huge deal unless you're already working in MPC or you're interested in MPC. How many machines do we actually have in our bank of machines to solve these problems? Well, our upper bounds will use at most this amount, which is slightly more than optimum, but it's not a ridiculous amount more than optimal. So we'll allow here n plus m over s machines. That's enough to assign one machine to each node of the input graph, and also to actually fit all the edges onto the over the whole bank of machines, which you have to be able to do to actually have the input graph on your machines. So it's not entirely optimal because we don't necessarily need n machines if our input graph is sparse, but it's pretty close to optimal for the upper bounds. And as I say, our algorithms use at most this, our algorithms use less than this. Lower bounds will be against any polynomial number of machines. So in particular, the lower bounds hold against the same regime as the upper bounds, but actually the lower bounds are stronger. They say even if you had n to the 10, n to the 50 machines, you still can't do better than this, whatever the lower bounds are going to say. Okay, so anyway, as I say, you don't need to think too much about that unless you're already working on MPC. But this is kind of close to the strongest case for both upper and lower bounds. Okay, so a more important thing about MPC is what this space bound S actually is, because this is the main restriction in the model. What can S be? Well, so some of the first work had a fairly high value of S, this high or superlinear space regime, where S is still obviously lower than the total size of the input, which can be as much as n squared, but it's polynomially higher than n. Okay, so n to the 1 plus epsilon, say, where epsilon is some positive constant. And in this regime, you can actually do a lot of stuff very quickly. I've only given one example here because there's quite a lot more stuff we can do even with more restricted space. But for example, you can solve maximal matching in only constant rounds in this high space model. And even if you restrict the space a bit to linear, or I guess quasi-linear here, so S equals n log n, say, so you can store n log n bit words, which would allow you to have a list of all the nodes in the graph, for example, or a list of all of the nodes neighbors in the graph. Even then, you can do quite a lot of stuff in constant rounds, or at least very quickly. And there's a node equivalent to congested clique for a certain kind of subset of problems. These aren't equivalent for all problems. If you're dealing with problems that require sending a huge amount of information around, like say matrix multiplication or triangle detection, that kind of thing, then these models do have differences. But for the kind of problems that I'm going to be talking about, this linear space regime is equivalent to congested clique, which is a distributed model but allowing all-to-all communication. And as I say, you can do a lot of stuff very quickly here still. So you can solve minimum spanning tree, you can solve L+1 coloring, you can find spanners. The first two you can solve even deterministically, the second is currently only randomized, but it seems very likely, again, that you could make that deterministic using the same techniques that the first two used to make it deterministic. So for both high and linear or quasi-linear space, really the sky is the limit here. We don't know much about kind of limitations. We don't really know what's stopping us from getting very fast algorithms for almost all problems. But the regime we're going to be looking at is the low space regime, often called strongly sublinear, where S is much lower. It's not n, so you can't store all the nodes in the graph. On a machine, it's n to the small constant, so n to an arbitrarily small positive constant. And this is no longer related to congested clique because you can't do a lot of the stuff you can do in congested clique, but instead it has this relationship to local, which is what's going to be the focus of this talk. So this is what I'm going to be talking about throughout the next however long we've got. And now there's kind of a cutoff here. You can do a lot less in constant rounds or even close to constant rounds. And really there seems to be a barrier here, which I'll talk about a bit later, exactly what this barrier is. But unlike in the linear space or the superlinear space regime, really there seems to be an inherent difficulty to getting algorithms that are faster than a certain particular point, which is related to how fast they are in the local model. Okay, so there's a big difference between the low space regime and the linear and superlinear space regimes in what we can really do here. And it's this low space regime that's going to be the focus of this talk. Okay, what kind of problems do we care about in these models, or at least for the purposes of talking about this link between the two models? So I'm going to first give a general kind of framework that the problems we're going to look at fall into, which is that we have our graph, and at the end of our algorithm, whether local or MPC, each node has to output some label. So this can be anything. It depends on what the problem actually is as to what the label means. And certain combinations over the whole graph of these output labels are going to be called valid. And that's the definition of the problem. You define your problem by which combinations of outputs are valid. And then the algorithm, whatever algorithm for the problem we have, just has to output a valid combination on whatever input graph it's given. Okay, and examples of this are maximal independent set and vertex coloring. These are the examples we're actually going to stick with for the rest of the talk. If you already know what these are, you can probably see how these fit into this framework. But actually, this is, yes, there's no real reason we have to restrict to vertex labeling. We could also define an edge labeling kind of framework, but also edges are allowed to output labels as well. And validity depends on edge labelings. So all of this stuff extends also to edge labeling problems like, say, maximal matching and edge coloring. But for simplicity, I'm just going to stick to vertex labeling. But there's no inherent reason why this has to be just about vertex labeling. It's just kind of a simple class of problems to consider. Okay, so our two kind of representative example problems are, as I say, going to be maximal independent set and vertex coloring. Probably a lot of people already know a lot about these problems, but I'll give a recap of what they are anyway. So maximal independent set. The output labels in maximal independent set are yes, I'm in the maximal independent set, or no, I'm not in the maximal independent set. So there are only two possible output labels. And there are some rules about what set of yes nodes is allowed to be for the output to be valid. So the first criterion is that it's independent, which means there are no two edges between any yes nodes. Okay, so no edge can have both its endpoints saying they're in the maximal independent set. And the second criterion is maximality, which means that no node could be added to the current maximal independent set and it still be independent. Or equivalently, every node that's saying no is adjacent to a yes node, because if it wasn't, then we could add it. Okay, so those are the criteria. And here are some examples of maximal independent sets. This is one with 4 nodes saying yes, they're in the maximal independent set. But here's another example where only 2 nodes are in the maximal independent set. So there's no fixed size that the maximal independent set has to be. You can find maximal independent sets usually of different sizes. It's not a maximal independent set, which is trying to find the largest possible one in the whole graph, which is a much harder problem and one you can't really do efficiently in most distributed or parallel settings. We just need a maximal independent set, of which there could be many different ones of different sizes. Some examples of things that aren't maximal independent sets are this, for example, all nodes in the graph. Here you have a lot of edges, such as this one, where both endpoints are yes, which breaks independence. Or this one here, we don't break independence, but we have a node here, which is a no node, and all its neighbors are no nodes. So that could have been added to the maximal independent set. So it wasn't maximal. Okay, that's maximal independent set. The other problem we're looking at is delta plus 1 coloring. So delta plus 1 coloring is another very well-known, well-studied problem. We have an input graph. Our output labels are going to be colors from a palette of size delta plus 1, where, if you recall, delta is the maximum degree in the graph. And each node has to choose a color from these delta plus 1 colors. And they have to do it in such a way that no two adjacent nodes choose the same color. So every edge has to have different colored endpoints. So it's called a proper coloring usually. This is an example of the coloring on this graph. The reason it's delta plus 1 here is because this means that there's a simple greedy algorithm for the problem sequentially. So if you just look at one node at a time, it has most delta neighbors, it has delta plus 1 colors to choose from. So even if all of its neighbors have already chosen a color, there's still at least one left in its list that it can choose. Okay, and the fact that this can be done greedily, it can be always a partial coloring can be extended to a full coloring, makes this problem very amenable to distributed and parallel algorithms. Okay, what's known about these problems in the local model? Well, here are the algorithmic running times for MIS and coloring in the local model. So randomized algorithms, we have this MIS algorithm by Ghaffari, which has a randomized part of log delta rounds and then a polylog log n finishing up part. And coloring, the randomized initial part is very quick, it's log star delta. So the running time is dominated just by this polylog log n. And that's due to Chang, Li, and Petty. For deterministic algorithms, both these problems have polylog n running times that follow naturally from Roshan and Ghaffari's polylog time network decomposition. And those are also used as black boxes in the second stage of the randomized algorithms on graphs, which are shattered into components of only polylogarithmic size. Okay, so those are the algorithms. Lower bounds, what's known about lower bounds? So for MIS, we have these recent lower bounds by Baliotal, which say that you can't beat both a running time of delta and log log n over log 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 n for randomized algorithms. And delta and log n over log log n for deterministic algorithm, it's the minimum of those two terms. So for some values of delta, you can beat one or the other term, but you can't beat both of those terms at the same time. And for coloring, we don't really have any bounds that are going to be relevant to us here. The only lower bound we have for coloring is log star n, which is much lower than the upper bounds, much lower than really, I guess we think the complexity should be. So on the lower bound side, I'm only going to really talk about MIS here because the lower bounds for coloring aren't strong enough to be relevant to this connection I'm going to be talking about. So yeah, for lower bounds, we have good bounds for MIS. We don't really have bounds for coloring. Okay, so having done the fundamentals, what is this connection that I'm going to spend my whole time talking about between local and low space MPC? So there's an upper bound side and a lower bound side. The upper bound side comes from a process called graph exponentiation. And what graph exponentiation allows us to do is take an algorithm from local and run it quickly in low space MPC. And the observation that allows us to do this is that a t-round local algorithm, so if you have a local algorithm on a graph, it takes t rounds, that's equivalent to having a process where nodes just see their t-radius neighborhood and then can make their output decision immediately, and these output decisions will all agree with each other. Okay, even though local is usually phrased as a message passing, round by round message passing model, and that's how I phrased it as well, it's actually equivalent to this more kind of fundamental property about the structure of the graph, where an algorithm is actually equivalent to just being able to see a ball and make a decision. And the way we exploit that in low space MPC is that we can just collect these balls onto machines so long as they fit in the memory of the machine. And we can do this quicker than just collecting it hop by hop. We can actually speed this up exponentially by this following process of graph exponentiation. We have a machine and we assign it some node V, and we do this for all nodes. So we give each node its own dedicated machine. And in the first round, we just collect all the edges that have V as an endpoint onto this machine that's dedicated to V. We can make copies of the edges. We don't have to do some editing. We don't have to think about trying to have machines for like both the endpoints of a particular edge. We just copy the edges if we need to. So we get all the edges that have an endpoint of V on this machine dedicated to V. And we do that for all the other nodes as well. They also have these one-hop neighborhoods for each node in the graph on a particular dedicated machine. And now this machine for V can go and ask all these neighbors, which it now knows, for their own one-hop neighborhoods. Because these neighbors have their own dedicated machines, this machine can just go and ask those machines to send their neighborhoods across. So in the next round, having done this, we now have the two-hop neighborhood of V, because we have the one-hop neighborhood of all the one-hop neighbors, that's the two-hop neighborhood. And now, if we repeat this process, now every machine has a two-hop neighborhood for its dedicated node. We ask the two-hop neighborhood for the two-hop neighborhood, we get the four-hop neighborhood. So you can see that if we repeat this process, then every round we're going to double the size of the neighborhood we have on the machines. So in only log t rounds, we get neighborhoods of radius t. And once we have neighborhoods of radius t, we can just run our local algorithm as a black box on this ball to get what these outputs should be. And we know that those outputs are all going to agree with each other, give a valid output for the whole graph. Okay, so that's the upper bound side. For lower bounds, we want a similar way of speeding things up exponentially, going from t to log t in complexity, going from local to low space MPC. And for that, there is this landmark theorem by Ghaffari, Kuhn, and Rito from Fox. I'll refer to this as GKU because I'll talk about it quite a bit. And this has quite a few technical details. I've already taken out some technical details, but still has some technical details, even in this paraphrase statement, which I'll go into later. So for now, all I'm going to say about this is basically that it says if you have a lower bound of t in the local model, then you can take it to a conditional lower bound of log t in the MPC, low space MPC model. By the way, at some point I'm going to forget to say low space MPC. So whenever I say MPC from now on, I mean low space MPC. So this is what we were kind of wanting as a counterpart to the graph exponentiation process. I said conditional lower bound, and I'll go into more detail about what I mean by conditional later, or what they mean by conditional. But for now, the upshot of this is that kind of what we expect when going from local to MPC is that upper bounds by the process of graph exponentiation go from t to log t rounds, and lower bounds by this theorem of GKU go from t to log t rounds, or at least omega of log t. So is it that simple? Do we have that if we have complexity of t for a problem in local, then we get complexity of log t in MPC? Well, the fact that I have quite a long time left in this talk should probably tell you, no, it's not going to be that simple. There are quite a lot of caveats to both these statements, the upper bound and the lower bound statements. Can't just be applied all the time. Both of them have fairly severe restrictions. And that's what we're going to look at now. So we'll start with the upper bound caveats. If we can we just do this for MIS, for example? What happens if I do this for MIS or coloring for that matter? We take our upper bounds in local, and we want to say, can we speed these up by an exponential factor, get log of those upper bounds in MPC? Well, there's one part in the graph exponentiation explanation, which I kind of skipped over, which you should already probably be suspicious of if you've already worked in MPC, which is that you can only actually do this process if these neighborhoods you're collecting, these t-radius neighborhoods, actually fit into the space on your machines. That only happens if delta to the t is at most s, which means that we don't get these running times without kind of an asterisk next to them in MPC. They have to come with these criteria about how high delta could be so that these neighborhoods actually fit into the space bound. And for the randomized algorithms, these are still non-trivial. You get these bounds, like say, for example, 2 to the root log n for MIS. But for the deterministic algorithms, basically, because the deterministic algorithm is polylog n, you just can't fit these balls in unless your graph only had degree of most 2. And this is pointless because we already actually have better algorithms for coloring cycles and paths. So the deterministic algorithms here are useless now. And the randomized ones have these severe restrictions. So can we get rid of these restrictions? And the answer to that question really depends on the specific problem that we're looking at. So to get rid of these restrictions, what we would want to do is somehow sparsify the graph. So reduce the degree to below this point where graph exponentiation can actually be done in some way that doesn't destroy the properties our algorithm needs to solve the problem. Can we do this? Well, actually for coloring, we can do this. So there is this paper by Chang et al. From 2019, which does some sparsification. It reduces an instance of coloring to a bunch of instances of lower degree. Not actually as simply as I've made it sound. It doesn't reduce single degree below the threshold in the previous page, but they do some other stuff to get around that. But what they get essentially is via some sparsification process, they get an exponential speed up. They get from polylog log n to order of triple log n, which is exactly what we were kind of hoping for from our very simplistic overview. The same is not true of MIS. So MIS, there is a paper that does sparsification and then something like graph exponentiation to efficiently solve MIS, but it doesn't manage to get an exponential speed up over the local running time. It only gets a speed up from log delta leading factor to a root log delta leading factor. O tilde of root of delta. And there seems to be a real barrier to be able to sparsify below that. In fact, this is something I've tried a bit myself. It seems like, as far as we know, we have no real way of sparsifying more than that and still getting MIS algorithms to actually work. So yeah, the message here is that in some cases you might be able to sparsify so you can run graph exponentiation, but really this is problem dependent, and the answer is probably mostly no. Coloring just has some properties that make it particularly amenable to sparsification, but I'd say most problems you probably aren't going to sparsify to the extent that you can get this exponential speed up. Okay, what about the lower bounds side? So we go back to lower bounds for MIS from the local model, Barlio et al.'s paper. What we want to get is an exponential speed up in these lower bounds, so a log factor of these expressions in the lower bounds. Do we get this from the theorem I showed you of GKU? Well, there are three kind of problems, or at least caveats, to applying this theorem. The first one, the least troublesome really, is this: is that the statement only allows lower bounds that depend on n. It doesn't allow for dependency on delta, and also it only allows randomized lower bounds. And if you go back to the previous slide, you'll see we were trying to apply this to a deterministic lower bound as well. This isn't a problem actually, because as we found, this is one of the things we did in one of our policy papers this year, you can extend this framework to include deterministic bounds and bounds that depend on delta. And in particular, you can include the bounds I had on the previous slide for MIS. So that's not a problem. This theory can be extended and has been extended to account for deterministic bounds and bounds that depend on delta. The second caveat is that, as I said, these are conditional lower bounds and not unconditional lower bounds. What that means is that if you have a T-round unconditional lower bound in local, it doesn't say you can't beat log T in MPC. What it says is that if you can beat log T in MPC, then you can solve this particular connectivity problem faster than we think should be possible. And what this problem is it's distinguishing whether your input graph is a single n node cycle or whether it's two n over 2 node cycles. You just have to distinguish between those two cases. Which seems like a simple problem, but people have tried it a lot, and we think it shouldn't be possible to do in less than log n rounds in low space MPC. And that's what the condition is on. And we know actually that we can't really hope for unconditional lower bounds, because that would imply a breakthrough in circuit complexity. That was one of the kind of early papers on MPC lower bounds. So a conditional lower bound is the best we can hope for, really, and this is quite a strong condition. Actually, people try this problem a lot. It's a pretty fundamental problem, and I think that the consensus is, and I also believe that there's no way of doing this faster than log n. So this is a pretty good condition on which to base lower bounds, I think, and the authors obviously thought so as well. And some condition of this kind is needed if we want non-trivial lower bounds. So this is something we really have to just live with. It's there, but at least in plenty of people's opinions, this isn't a major drawback because we believe the condition. Okay, what's the third caveat? The third caveat is this component stable term here, which I haven't talked about at all so far. So these lower bounds that you get out the other end of this framework don't apply to all algorithms. They just apply to algorithms that have this component stability property. And originally this was thought to only be a technicality. So there's a statement in this paper that says all known MPC algorithms are either component stable or could easily be made component stable without worsening their running values really at all. But it was kind of a new concept, so there wasn't really kind of much thought about what this meant for algorithms. And this was really the focus of one of our policy papers. So what is component stability? Is this actually a restriction on algorithms, or is it just a technicality? So I'll go into the definition first. So the original definition that GKU gave for component stability is that we have our graph here. We're meant to be providing an output for all nodes, but in particular, we'll consider this particular node here to provide an output for. And an algorithm that gives an output for this node is component stable if and only if the output for the nodes depend only on their connected component, so the topology of this connected component, the purple one here in this example, and the IDs of the nodes in that connected component, and the shared randomness that we have for a randomized MPC algorithm. So this is kind of a technical point, but unlike in local where nodes have their own randomness, in MPC it only makes sense to have shared randomness because the nodes are on entities, your entities are a bunch of computers. So we have shared randomness here. And a component stable algorithm was allowed to depend on this connected component that the node's in, and the shared randomness. So one of the things we found is that this definition is actually very fragile, and really you actually need to include something else in this definition, which is that you have to allow the outputs to depend on the value of n. And in fact, not just some estimate of the value of n, as people usually do in local, but the exact value, because unlike in local, this is something that MPC algorithms can find immediately. So you have a constant round algorithm that can count the number of nodes in the graph and tell it to all the machines. So MPC algorithms know the exact value of n, and it makes sense that they would then use it. And in fact, like if they don't use it, then it doesn't really include most known algorithms. So you really have to extend this definition to include dependency on the exact value of n. But this required a few changes to proofs. In particular, one thing you have to note is that we found that you couldn't get a result along the lines of GKU for all problems, but you have to slightly restrict the class of problems. But you only have to restrict it to a class that doesn't really rule out any problems of interest. So essentially, the moral of our body paper was that you can get a lower bound lifting framework along the lines of the theorem I showed you from GKU with this definition of component stability that still gives you this lifting lower bounds from local to low space MPC at an exponential speed. And that's what component stability means here. Dependency only on your connected component, shared randomness, and the exact value of n. Okay, so how much should component stability hinder your algorithms? How much should component instability help? Should it really help us to use different connected components? That's what component stability is ruling out here. It's saying you can't use information from other connected components other than just the number of nodes. You're allowed to use the number of nodes. You're not allowed to use like what edges there are in these other connected components or anything like that. Should that really help us? So for example, if we're trying to solve MIS, Maximal Independent Set, and we need a solution for U, does it help us to use information about V, V's neighbors? You'd have thought the answer should really be no. For the following reason, if we have a valid maximal independent set across this whole graph, and we change the maximal independent set, say in the orange component, the one that V's in, or in fact we change the edges in the orange component and then another valid maximal independent set within that component gets recalculated, that doesn't affect the validity of the solution in the purple component at all. So the basically solution validity is already component-wise. So really you would have thought for a problem like MIS or indeed for delta plus one coloring, it shouldn't help you to see information about what edges are in V's component so long as it's in a different component and the number of nodes doesn't change. Okay, is that really the case? And that's what the next section is going to be about. But we're going to start from a slightly strange direction, or it might seem strange to begin with. And that's, we're going to take a detour to derandomization in MPC. This is what we were thinking about in 2019 with Artichuma and Marav Bhatta. We were trying to do derandomization in MPC. And that means just taking a randomized MPC algorithm and trying to turn it into a deterministic MPC algorithm as quickly as possible, ideally without any slowdown in the time. What randomization techniques can we, derandomization techniques can we use? Well, the obvious thing to use is a well-known and well-used in a lot of different situations, derandomization technique called the method of conditional expectations. And what the method of conditional expectations is if you have a randomized process using random seed, so actually you can think of a randomized process as a deterministic process, but that it gets some randomness as input, and this randomness as input is what I'm calling the random seed. Then the method of conditional expectations is a process of agreeing globally on a particular one of the possible random seeds you could have got to use, and then to kind of simulate the randomized algorithm using that random seed. And you can do this, and it gives you a deterministic process with a result that's at least as good as the expectation was under your randomized algorithm. Okay, and in particular, this can be done quite efficiently. So if your randomized process was only constant rounds and your random seed was only order of log n bits long, then you can get your deterministic process at the other end to also only be constant rounds. Okay, so I'm not going to talk really about how to get short random seeds. I'll just say that there are other techniques often used in derandomization to get your random seed requirements as low as possible. These include families of bounded independence hash functions and pseudo-random generators. Both of these have some drawbacks, some conditions to their use, so you can't just throw them in every problem. You often have to do something a bit cleverer or use some combination of these. But there are ways of reducing your seed length for on a kind of problem by problem basis to this log n bit length for many problems. Okay, so doing this in MPC, how do we do this in MPC? Well, there was this existing paper on congested clique that did an implementation of the method of conditional expectations by Sensor Hillel, Parter, and Schwartzman. And as I said, the congested clique is strongly related, equivalent under certain circumstances, to linear space MPC. And we showed that this could be adapted to low space MPC and still have these very efficient properties of, that basically doesn't give you any slowdown as long as your C's are any log n length. And we use this a bunch of times for various different problems, various different reasons in our recent 4 papers. And we're going to see one example of this, which is going to kind of connect back to what we were talking about before. Hopefully you remember what we were talking about before. And what we're going to look at is applying this to MIS. So if you remember, we had this kind of unsatisfactory graph exponentiation thing here, which was telling us we have this MIS algorithm, the Davies MIS algorithm, in local. We want to run graph exponentiation to speed this up by an exponential factor in low space MPC, but we have this ugly degree condition here for which we need degree to be below 2 to the error of root log n to actually do this. Now, I don't really care about sparsification for this part of the talk, so I'm going to get rid of this condition by just saying, for now, I'm going to fix delta to be log n, or at most. Okay, I can do this because the upper bound, let's see, it holds for any delta, so we're just plugging in a particular value of delta here, and if we plug in this particular value of delta, we get rid of this condition because this value of delta was below the threshold that we needed to use graph exponentiation, and also these running times simplify to just polylog n in local and triple log n in MPC. Okay. So we have a randomized MPC algorithm that solves MIS in triple log n rounds when delta is at most log n. And then we showed in our body paper, among other things, we didn't kind of show specifically, but it's a consequence. Some of the things we showed that if you apply the method of conditional expectations with a pseudo-random generator, you can de-randomize this and get a deterministic algorithm in triple log n rounds in MPC for MIS when delta is at most log n. But now if we look at the lower bound we have for MIS, we had this MIS lower bound here, which is coming from Value et al.'s paper and with our framework for lifting lower bounds from local to MPC applied to it. We get this conditional component stable lower bound, which is minimum of log delta and log n. And when you plug in delta equals log n, you get that this is saying that you shouldn't be able to do MIS in less than log n rounds. And these don't seem to agree with each other here, right? We have an upper bound of triple log n, log n, and a lower bound of log n. So what's gone wrong here? This shouldn't be right. What's happened? Well, actually, both of these statements are correct. We haven't done anything wrong. But the lower bound, if you remember, was against component stable algorithms, and the method of conditional expectations, it turns out, is inherently component unstable. So why is that? If I get the method of conditional expectations back up, we can see that it involves globally agreeing on a good random seed to use. And globally means across all nodes, in particular across nodes that are in different connected components. They still talk to each other during this process of agreeing on a global random seed to use. And that means we do have this property that this algorithm uses information from other connected components to get the output for a particular node. Okay, and that's why these bounds are both true, can be both true. And the upshot of this is that component instability does help with deterministic algorithms. And in fact, it helps for a lot of deterministic algorithms. This wasn't kind of cherry picking situation. It helps for MIS, it helps for maximal matching, it helps with the low-hash local lemma and a bunch of related problems to the low-hash local lemma, such as sequence orientation or edge coloring with fewer edges than the greedy algorithm. It also helps for delta plus one coloring, but in that, and this is the second body paper we had this year, but that doesn't break or surpass the component stable lower bound, but it does give you a triple log n deterministic algorithm when the local algorithm is only log n. So it gives you a doubly exponential speed up from the local algorithm, but as I say, there's no equivalent lower bound, so it doesn't break the lower bound. So the moral here is that actually component stability helps for a lot of deterministic algorithms. I'd say actually most deterministic problems, most algorithms for deterministic algorithms for problems are helped by component instability. So these lower bounds you get against component stable algorithms really aren't very watertight deterministically. Okay, but now the really surprising thing is that if we look at a slightly different problem, so instead of maximal independent set, now we're going to instead weaken the problem slightly so that we don't care about maximality anymore. We just care about the size of the independent set we find. And we want an independent set of size omega of n over delta. Why that size? Because you can, if you think about it a bit, you'll see that any maximal independent set has to have at least this size. The reason for that is that if you find a maximal independent set, say by a greedy algorithm, every node you add to the independent set removes its neighbors from contention. They can't be in it anymore. But that's at most delta nodes, because every node has at most degree delta. And that means you can carry on adding nodes at least n over delta time before you run out of possible nodes. Okay, so any maximal independent set has size n over delta. But this is a weaker requirement now, because you can also find non-maximal independent sets probably that have size n over delta. Okay, so slightly weaker, slightly easier problem. What's known about this problem? Well, if we apply Luby's algorithm, now Luby's algorithm is kind of the standard MIS algorithm. What it does basically is just repeatedly have each node choose some priority and then join the MIS if it has the lowest priority out of all its neighbors. Usually you need to run log n iterations of Luby's algorithm, or log n iterations, to solve the MIS problem, to get a maximal independent set. I mean, that's still true here, but actually if you just run the first iteration, you just run one iteration of Luby's algorithm, then it already gives you an independent set of this size, n over delta size, in expectation. Okay, so we solve this problem in expectation in only a constant number of rounds in randomized, just by applying Luby's algorithm, stopping after one iteration. What about lower bounds? Well, there's this recent lower bound by Kowabayashi et al. That says you can't solve this problem with high probability in less than log star n rounds in local. Why do these lower bounds seem to disagree with each other? Well, just because with high probability is a stronger criterion than expectation. So that's running one round of Luby's algorithm solves the problem with in expectation, but it doesn't solve it with high probability. Okay, so these bounds are not against each other. They are mutually compatible. If we apply the lower bound lifting framework to this lower bound by Kowabayashi et al., we get a lower bound in low space MPC, conditional, again, and against component-stable algorithms. Say you can't do faster than log star n, which is pretty low, but it's still higher than constant. But now if we go back to the algorithms, what we can do is to get from local to MPC, we can do a very simple sparsification where basically we just subsample all the nodes in the graph with some particular probability in order to actually be able to fit balls of whatever size we need into our machine space. We only need balls of constant radius, which means that we can run this algorithm basically in constant rounds in MPC as well, just by doing this very simple sparsification step first. And then we can de-randomize this using the method for conditional expectations and some constant-wise independent hash functions. It was already well known, in fact, it was in Luby's original paper, that Luby's algorithm only needs pairwise independence. And the sparsification step, we can also de-randomize using only constant-wise independence. To get a deterministic algorithm that also only takes constant rounds for this one. But now we have an issue. We have some conflict here because our deterministic algorithm now is stronger. It's saying we get this with certainty, not just an expectation. And the reason for that, as I say, is that the method of conditional expectations gives you deterministically what your randomized algorithm had in expectation. So this is kind of exactly what we needed here. And that's a stronger criterion, it's a stronger property than the lower bound is saying should be possible. The lower bound is saying you can't even get a constant round algorithm with high probability. We've got one with certainty. So what's the solution? How is this possible? Well, we already know that. It's because the lower bound is only against component-stable algorithms, and we used the method of conditional expectations, which made our algorithm component unstable. But the surprising thing here is that this deterministic algorithm we got didn't just beat the deterministic lower bound, it actually beat the randomized lower bound. So component instability also helps for randomized algorithms. Okay, we've cheated slightly because the algorithm we got was deterministic. But what I mean here is that it allowed us to break the randomized lower bound by exploiting component instability. So now it seems like component instability really does help MPC algorithms. We've got deterministic examples, we've got randomized example. So these lower bounds that we get from this lifting framework really aren't very watertight. And if we go back to our final overview, what we have here is that we were asking whether it's true that a T-round complexity in local gives you a log T-round complexity in MPC. And the answer is basically not really, because on the upper bound side, we have to be able to do sparsification as this big hurdle to the graph exponentiation procedure, which we probably can't do to this extent to get this exponential speed up for most problems of interest. And on the lower bound side, we have this lower bound lifting framework, but it only gives us lower bounds against component stable algorithms. And we've seen a lot of examples now where component instability can actually help us and surpass these lower bounds. Okay, so this seems pretty bad. It seems like we've got quite a lot of work left to do. And I don't have much time left in this talk because most of that work is still not being done. But it's not quite as bad as it seems. So if you want to work on this problem, this connection, here is what we don't know. So for upper bounds, basically, we want to know which problems can we get this exponential speed up, which problems can we achieve this log of local time in MPC. And as I say, we can do it for coloring, but really for most of the problems, we can't do that yet. But we have, I mean, I'd say it's very hard to do this for MIS and maximal matching, but there's nothing saying it can't be done. Similarly, for a bunch of other problems, you could try and do this. And we don't really know what makes problems open to sparsification in general and what stops problems from being actually sparsified. So that's what we can study on the upper bound side. On the lower bound side, I made it sound very pessimistic about these component stable lower bounds. But actually, while we have a bunch of examples of deterministic algorithms that beat the component stable lower bounds, we have very few examples of randomized algorithms, so beating the randomized lower bounds. So we really only have this one example and probably a couple of related problems, which essentially would be essentially the same proof. What we don't have is an example of a randomized locally checkable problem for which we can exploit component instability to beat the component stable lower bound. What do I mean by locally checkable? I mean that, so we have a node V, we need to give an output for this node. And now there's a concept of output validity per node. So before, problems were only defined by like valid configurations over the whole network. Now there's some concept of a node's individual output being valid. And the validity of an output has to be checkable by only seeing a small radius ball around V. So we should be able to say, look at the two hop neighborhood around V and say, yeah, V's output, whatever it's given, is valid. That doesn't necessarily mean the whole output in the graph is valid. But V's output, we should be able to check by seeing a ball around V. The radius of this ball is usually defined to be constant when you're talking about locally checkable problems, but actually even for something much weaker, even if we were allowed to see the whole connected component of V to validate its output, we still don't have an example of that kind of problem for which we can exploit component instability. And then the outputs over the whole graph is valid, so the output of the whole algorithm is valid if every node's output is individually valid, which, as I say, we can check by looking at these small radius balls. And this includes problems, in fact, including the ones we were talking about the whole talk. So MIS and coloring, both of these are locally checkable. Both can be checked by only seeing the one hop radius. So coloring is quite obvious to see that if you just check all of these neighbors, check that none of them color themselves the same color as V, then V's output is valid. If you do that for all nodes in the graph, then the whole thing's a valid coloring, a proper coloring. MIS is slightly more, I guess, hard to see how you check these outputs, but you check basically the properties of maximality and the properties of independence. For maximality, you can just check that if V didn't put itself in the independent set, then at least one of its neighbors had to. Okay, so you just check that if V said, no, I'm not in the independent set, then one of these neighbors has to have said, yes, I'm in the independent set. Otherwise, V's output's not valid because it could have added itself to the independent set, so the independent set's not maximal. And you also have to check independence. So you just have to check that if V said it is in the independent set, then none of its neighbors said they were in the independent set. If you check both those things, all nodes, then your overall solution has to be a valid MIS. So again, that problem is radius 1 checkable. And we don't have examples of that problem. So the example we had wasn't MIS, it was this weakened problem. We don't have examples of locally checkable problems for which exploiting component instability allows us to beat the bounds we get from this lower bound lifting framework. So we have no examples of beating these bounds at all. And in fact, if we had to conjecture, we would probably actually say that we think these bounds really should hold against all algorithms, but we don't really know how, because this component-stability thing is kind of quite an inherent part of the proof. So we haven't been able to prove that, but we actually think that these bounds are fairly robust. Okay, but so this is kind of the main open problem if you want to think about the connection between local and MPC. Is it true that these bounds actually hold against all algorithms, or can we find an example of an algorithm which exploits component instability to break these bounds, surpass these bounds for a randomized locally checkable problem? Okay, and yeah, that's the main thing I'll leave you with. I think that's the most interesting question in this area. So that's all about the connection between local and node-based MPC. Thanks for watching, and hopefully I'll see you at the live talk to answer any questions. Thank you.